So hello everyone. So basically we will talk about graphs today. We will talk about DFS and BFS in a graph today. So if you don't know what is a graph, so let us say that you are given two nodes, means not two nodes, you are given some nodes and there are relations between these nodes. So what I mean to say here is that, so let's say this node is connected to this and it is also connected to this node. Again, this node is connected to this and this node. Okay, so if I want to give a real life example, so let's say there are four persons in a room. So let's say this person knows or has friend, means is a friend of this person and this person. So this person A, let's say this person A has a friendship with person B and C. Similarly, person D also has friendships with person B and C. The person C has friendships with A and D, and person B has friendships with A and D. So if there is a relationship between two nodes, we connect them by an edge. So this is an edge, and like this we make relationships between two nodes. So basically this is a brief idea of a graph. So let us now look at that how can we traverse the graph, means how can we go through the nodes of a graph, means how can we explore all the nodes of a graph. Okay, so let's say you are given this graph which I have just drawn. Okay, so let's say we are starting at node A. Okay, and we want to explore all the other three nodes starting from A. Now basically there are two types of traversals, DFS and BFS. Okay, so basically DFS is basically depth first search and BFS is breadth first search. Okay, so in DFS we use a LIFO system, and uh, in BFS we use a FIFO system. Okay, means in DFS we use a stack and in BFS we use a queue. Okay, so basically if we are starting at A, so in DFS the algorithm of DFS says that we will keep on traversing all the neighbors till we have no more neighbors. So okay, so we will start from A. So let's say we go to the neighbor of A, let's say any one neighbor. So let's say we go to B. So now we will go to another neighbor of B. Okay, means we will not go to the neighbor of A. So that is the main difference between a DFS and a BFS. In BFS we would first explore all the neighbors of A before going to the other neighbors of B. But in DFS, which we are doing currently now, so we are doing DFS now. So in DFS, when we are the when we have gone to B, we will explore the neighbors of B, not the neighbors of A. So as we can see that B has another neighbor D, so we will go to D. Now using the same algorithm as we have used before, we will now explore another, means we will explore the neighbors of D. So D has another neighbor C. Okay, so we will go to C. Okay, so when we go to C, we see that the neighbors of C are A and D, but we have already explored A and D before, so we will not explore them again because we have already explored them. Okay, so now now as we can see that the neighbors of C are already explored, so we come back to D now. Okay, so apart from C, there was one more neighbor of D, that was B. So B has also been explored again. So there is no more neighbors of D left to be explored. So we come back to B. So B has two neighbors A and D. So both of them are also explored. So we again come back to A, and the neighbors of A are also explored. So basically our DFS is over here because we have explored all the nodes. Okay, so if I take another example which will be easier to understand, so let us take this example. So you are given a graph like this. So let's say this is A, B, C, D, E, F and G. Okay, so let us say that you want to traverse all the nodes, so you are starting from A. Okay, so we will use a stack in DFS as I have told before. So let us maintain a stack. So stack is last in first out. So we have A in the stack currently. Okay, because we have explored A. So now we will go to one neighbor of B, any one neighbor. So let us say that it is B. Okay, so we will push B into the stack. Okay, so what we do in DFS is that we take the neighbor of the last element in the stack. Okay, means the unexplored neighbor, means the neighbors which hasn't been explored till now of the last element of the stack. Okay, so the last element of the stack is B. So B has two unexplored neighbors, that is D and E. So we will take any one. You can take any one. Okay, so it depends on the graph given. Okay, so you can take D also, you can take E also. Okay, so let us take say that we are taking D. So we will push D into the stack. So now D doesn't have any more neighbors which are unexplored. D has a neighbor B which we have already visited. So D doesn't have any other neighbor which is unexplored. So we will pop D out from the stack. So our stack is now A and B. Okay, so we will go to the next. So now our last element in the stack is B. So we will see for an unexplored neighbor of B. So we have two neighbors of B, that is D and E, but D has already been explored. So we will go to E. So we will add E to the stack. Also, we will keep a track of the DFS order. So first we have explored A, then we have explored B, then we have explored D. Now we are exploring E. Okay, so again E doesn't have any means unexplored neighbors, so we will pop out E from the stack and we will go to B again. So E is popped out. So now the last element is B. So observe here that B now doesn't have any unexplored neighbor, means all the neighbors of B, that is D, E and A, has already been explored, right? So there is no more unexplored neighbor. So we will pop out B also. Now we have only A in the stack. Okay, so now we have only A. So we will go to the next unexplored neighbor of B, that is C. So we will put C in the stack. Now we will take the neighbors of C which are not yet explored. So one of the neighbors is F, another neighbor is G. So let us say that we are taking G. Okay, you can take F also. So what we have explored after E, that is C and G now. Okay, so G doesn't have any more unexplored neighbors. Okay, so we pop out G and our last element is now again C. So C has one more unexplored neighbor, that is F. So we put it in the stack, that is we put F in the stack. Okay, so we have explored F here. So F again doesn't have any unexplored neighbors, so we pop out F. Now we go to C. C now doesn't have any unexplored neighbor because all the three neighbors F, G and A has already been explored. So we pop out C and we go to A. So here A again doesn't have any unexplored neighbors because we have two neighbors, that is B and C. They have already been explored. So we will pop out A also. Now we have an empty stack. So we have an empty stack, so that means we have explored all the nodes of the graph. So we can stop our algorithm here. So the DF, the order in which we have traversed the nodes are given by this, that is A, B, D, E, C, G, F. So this is the DFS order. So one important thing is that our graph can have more than one DFS orders. Okay, so if I have traversed D before E, means if we have gone to E before D, so our order could have been A, B, E, D, C, G, F. Okay, so our graph can have more than one DFS orders. Okay, so I hope like how we do DFS clearly. So DFS can be done in two ways, using recursion and using a simple stack, just as I have told. Okay, so you can do in any one of the ways. Now if we go to the next traversal technique, so that is BFS. Okay, so in BFS, instead of exploring the neighbor of the last node, we explore the neighbor of the first node in the queue. So let us take the previous example only, so that it is easier for you to compare the two mechanisms. So that is the nodes where A, B, C, then B is connected to D and E, and C is connected to G and F. Okay, so if I have to apply BFS on this graph, so we maintain a queue here. Okay, so we maintain a queue here. So in queue we push from the end and we take out from the beginning. Okay, so initially our queue is empty, so we push A in the uh, queue. So basically we have A, so our BFS order has started, so we have A now. So the first element in the queue is A, so we will traverse one of the neighbor of uh, we will traverse all the neighbors of B. Okay, so not one, so that is another difference. So we will take all the unexplored neighbors of A. So we have two unexplored neighbors, that is B and C. So we will add B and C in the queue. Okay, so we have taken out A because A has already been explored. Now we have B and C in the queue. So the first element in the queue is again B. So we will again add the unexplored neighbors of B at the end of the queue. So the queue becomes B, C, D, E. Okay, so now we have this queue and B comes out of the queue. So now we have C at the front. So our so B has come out, so we will add B to the order, means the order in which we are traversing. So now the first node in the queue is C. So C has two unexplored nodes, that is G and F. So we are adding G and F. Okay, so we are adding G and F. So and then we are taking out C also. Okay, then our first node will be D. So D doesn't have any unexplored neighbors because there is one neighbor of B, but that has already been explored. Okay, so we take out D and add here. Similarly, E doesn't have any unexplored neighbors, so we take E. Then we take G and F. Okay, so after taking out F, our queue is empty, so we finish our BFS and the order is this. Okay, so again a graph can have more than one BFS order. So for example, if I had inserted C before uh, B here, means I would have taken the graph like, means the queue like this, that I have inserted C, the neighbor C before B. So in that case, C would occur before B in the final order. Okay, so a graph can have more than one BFS orders. And the most important thing you have to notice in BFS is that if you notice the levels of the graph here, so let's say A is present. So let's say we are starting from a particular node. Okay, so let's say the distance of A from A is 0 because A is present at the same position of A. So the distance from A to A is 0. Now the distance from A to B is 1 because there is one edge from A to B. Similarly, the distance from A to C is again 1, and the distance of DE GF is 2 each. Okay, means there is a distance of 2 from A to D, A to E, A to G, and A to F. Okay, so observe that in any BFS order, means in any kind of BFS order, means if you are doing a BFS and you traverse the nodes, so there can be more than one, but in every BFS order, uh, the nodes B and C will occur before the nodes D, E, G, F. So what I mean to say here is that the nodes which are closer to A, means the nodes which are present uh, closer to A will have means will be present before D, E, G, F. Okay, means B and C will be present before D, E, G, F. Okay, so see that B and C are present before D, E, G, F. Okay, so in BFS, you will process or you will visit the nodes which are closer to your source. So the source is the node you are starting with. Okay, so you are starting with A, so A is your source. So the nodes which are closer to your source, means B and C are closer to your source than D, E, G, F. So B and C will be visited before uh, D, E, G, F in a graph. So that is the speciality of BFS, that the closer nodes, you can surely tell that the closer nodes will be visited before the nodes which are farther. Okay, so that is the speciality of a BFS. Okay, so I think DFS and BFS are the two common traversal techniques, and we have seen that how to do both of them. So first of all, these are the two basic traversal techniques, and you should do some problems on them. So one of the best ways of doing DFS and BFS problems are in lead code. So if you go to lead code and search problems on DFS and BFS, you will get a lot of problems, and I think that will be better for, means that will give you a better understanding. So that's the two traversal techniques, basic traversal techniques. Now we will see a bit more advanced BFS. So there are one BFS named 01 BFS, and we will also see another traversal technique for finding the shortest path, that is the extra. So let us see what is 01 BFS. So I hope you have understood this BFS. So now let us see what is 01 BFS. Okay, so let us say that uh, you are given a graph, and the what happens in BFS is that the weights of the graph are similar. Means what the graph I means drew before, all the weights has a similar value or has no value. Means we can apply BFS only for a unweighted graph. Okay, just a minute. So we can draw means we can apply BFS for finding the shortest path for only a unweighted graph. Why we can use BFS for the shortest path problem? Because as I told that in BFS, we visit the nodes which are closer to the source before the nodes which are farther, means which are more distant from the source. Okay, so but BFS has a limitation that all the edges should have a similar weight, or all the means or all the means or the graph should be unweighted. Okay, but let's say you are given a graph in which there are two types of weight. So what I mean to say here is that the weights has two type, means the edges has either of two types of weight, means either the edge has a weight of A or the edge has a weight of B. Okay, means let's say that either the edge has a weight of 0 or the weight of the edge is 1. Means some edges have a weight of 0 and some edges has a weight of 1. Okay, so let's say that this edge has a weight of 0 and this edge has a weight of 1. Similarly, this edge has a weight of 1, this has also 1, this edge has a weight of 0, and this edge has a weight of 1. Okay, so if you calculate the distance of the nodes from A, so this let's say this is B, C, D, E, F and G. Okay, so the distance of B is 0, distance of C is 1, distance of F is 1, distance of G is 2, distance of D is 1 and distance of E is also 1. Okay. So as I told that in BFS, we visit the nodes having a lesser distance before the nodes having a greater distance. So B should be uh, means we should visit B before the nodes C, F, uh, D and E, right? Before visiting C, F, D, E, we should visit B because B has a lesser distance than these four nodes. Similarly, we should visit G at last because it has the largest distance from A. Okay, so we will start from A. So the uh, only difference between a BFS and a 0 1 BFS means if you see the algorithm, so there is only one line of means there is a change in only one line. Okay, so let us see what the change is. So if I maintain a queue for this graph, so I have to maintain a double-ended queue. Okay, so what I need to do here is that we need to maintain our data structure such that we can add from the end and we can also add from the front. Okay, so it will be a double-ended queue, not a means single queue, means one-ended queue. Means we should be able to insert from both sides, that is from the end and also from the front. Okay, and we need to take out the first element as we have done before. Okay, so if we see this, means if we make the queue, so our graph was A, B, D, E, C, uh, F, and G. So this was 0, this was 1, 1, 1, 0, and 1. Okay. So first of all, we are starting from A. So we will add A. So we were adding A now. Now the thing is that if the edge has a weight of 0, then we will add from the front, and if the edge has a weight of 1, we will add from the end. So if we will now see the neighbors, so the two neighbors are B and C. Okay, so B has a edge of 0, so B will be added in the front. So we will first take out A because we have already visited A. Okay, so we have already visited A. So now the queue is empty. Now we are processing B. So B has a means the edge between A and B is 0. So we will add B from the front. So B has the front position. Now C has a weight, means the edge between A and C is 1. So we will add C from the end. So that is C. So if we keep a track of the order here, so our order will be first we have visited A. Okay, now again we will take out the front element, so we take out B. So now our queue is C, means the front element is C, and we add B here. Now if you see the uh, neighbors of C, so that is F and G. So F has a weight of 0, so F will be added in front. Okay, sorry, I made a mistake. So we have to add the neighbors of B. Okay, so this was a mistake. So when we take out B, so we have to add the neighbors of B. So B has two neighbors, that is D and E. Okay, so both of them has a weight of 1, so both of them will be added at the end. Okay, and we take out B and we write it here. Now the first element is C, so we take out C now. Okay, so we take out C and we add the neighbors of C now. So our current uh, queue consists of D and E. So if we see the neighbors of C, so there are two neighbors, F and G. So F has a weight edge connecting of weight 0. So F will be added in front before D and E, because the weight edge is 0, so it should be visited before the other nodes because it has a lesser distance. Okay, so it should be added in the front so that we can visit it earlier. Okay, so we add F to the front and we add G to the end because the weightage is 1. Okay, so and we add C here. Now we take out F doesn't have any neighbors, so we pop out F. Then we pop out D because D doesn't have any other neighbors. Then E and G. Okay, so if we see the order here, that A has a distance of 0 from the source because it is the source itself. So A has a distance of 0. Now B has a distance of 0 because there is an edge of 0 from A to B. Okay. Similarly, C has a distance of 1. If I see, next we go to F. F has a distance of again 1. Okay. Now D has a distance of 1, E has a distance of 1, and G has a distance of 2. So you can see that since A and B has a distance of 0, so they are the closest nodes to the source. So they have been visited before the other nodes. Okay. Similarly, the nodes C, F, D, E, so they all have a distance of 1. So they all have, means the all the nodes having a distance of 1 are visited before G because G is farther than these four nodes. Okay, so we have visited C, F, D, E, and now we at the end we have visited G because it is the furthest node from G. So the only difference here is that in normal BFS you always add from the end, and in 01 BFS the difference is that if the edge weight is 0, you add from the front. If the edge weight is 1, you add from the end. So this is the only difference. Other things are exactly same as the normal BFS. Okay, so uh, I think we should now go for the Dijkstra algorithm. So let's say in a graph, it cannot, means it will always not happen that the edges are only of 0 and 1. Okay, so it can happen that the edges have a greater means has other weights also, means there are more than two weights. Okay, means there can be 10, means if the weight graph has m edges, so there can be m weights, means every edge has a different weight. Okay, so in that case we will use Dijkstra. Okay, so the penalty for using Dijkstra here is that the time complexity of Dijkstra is more than BFS. So the time complexity of BFS is O of V. Okay, so where V is the number of vertices and E is the number of edges. Similarly, for 01 BFS, the time complexity is the same. For DFS also, it is V plus E. Similarly, but for Dijkstra, the time complexity is V plus E log E. Okay, means there is a extra factor of log, means the time complexity goes up. Okay, so but you can use Dijkstra in case there is a weighted graph. Okay, so now what is the algorithm of Dijkstra? So let us say that you are given a graph. So let us take our previous graph. So this is D, E, C, F, and G. Okay, so let us take another edge from D to E. Okay, because this will be easier for you to understand. So let us assign some edge weights to the graph. So let us say this is 1, this is 2, this is 4, this is 1, this is 1, and this is 0, and this is 5. Okay, so what means the nodes which are closer to A or the source should be visited before, means should be visited earlier. So the only difference between BFS and Dijkstra is that in BFS we use a queue. Okay, means we add from the front or from the end of the queue, and we take out the first element. So in BFS we use a queue, but in Dijkstra we use a heap or a ordered set. Okay, so it is better to use a heap or a priority queue. Okay, so in priority queue we will maintain the nodes. So let's say we have a priority queue. In this priority queue, we will maintain the nodes in the order of their distances. Means the first element in the priority queue will be the node which has the lowest distance from the source. Means let's say we have explored some nodes. So out of all the nodes explored, so the first element of the priority queue will contain the node which is closest to the source out of all the nodes we have explored till now. Okay, so we have to maintain another array distance which will store the current distance of the nodes. Okay, so let us say that this is our distance array. Okay, so initially we have how many nodes? We have 7 nodes. Okay, so 1 2 3 4 5 6 and 7. Okay, so let us say that A is denoted by 0, B is 1, C is 2, D is 3, E is 4, F is 5, G is 6. So initially A, all of them are has an infinite value. So let's say we initialize all of the values as infinity. Okay, we will update our distance array at the end. Okay, so initially all of them are empty, so we insert, so let's say this is infinity for everyone. Okay, so I denotes infinite value. So we first insert the source. So when we are inserting the source, so the source will always have a distance of 0, right? So we update it as 0. Okay, so initially the priority queue is empty, so we push the source to the priority queue. So we will push the nodes in this manner that we will push the distance of the node and the node. Okay, and this is a priority queue. Okay, so we will first push 0 comma a in the priority queue. Okay, similarly as we have done before, we will take out the first element in the priority queue. We have taken out a, so now we will insert the neighbors of a. So the neighbors of a are b and c. So the distance of b will be distance of a plus 1, because we can reach b from a using one more distance. So the distance of b will be a plus 1. So uh, distance of a was 0, so distance of b will be 1. So this distance of b is 1, and the distance of c will be 2. Now which has a lesser distance? Obviously b. So in a priority queue, we take the, means we store the nodes in the increasing order of their distances, such that the node which is closest to the source is maintained at the beginning. So when we take out a, we add in this manner. So first we add 1 comma b, and then we add 2 comma c. Okay, so we have now this priority queue. Now we will again take out the first element, so that is 1 comma b. So now we have uh, then we will consider the neighbors of b. So that is d and e. Okay, so the distance of d will be distance of b plus 4, and the distance of e will be distance of b plus 1. Okay, so we will also update the distance of b. So the distance of b is 1. So when we take out a element from the priority queue, we will also update its distance. Okay, so the distance of d will be 5 comma, means 5, and the distance of e will be 2. Okay, so out of, so if we have to arrange the elements in the queue, so if I uh, clean this up, so now we have in the queue that is 1 comma just a minute. So yeah, so now we have in the queue 2 comma c, 5 means what are the nodes that we have explored. So let me draw the graph again. Okay, so it will be easier to understand. So this is D, E, F and G. Okay. So this was 1, this was 2, 4, 1. This was again 1, and this one's 1, 1. Okay. So now what are the elements in the priority queue? That is 2 comma C. Then we have 5 comma D, and again we have 2 comma E. So if I have to arrange these elements in the increasing order of their distances, so first we have 2 comma C, then we have 2 comma E, and then we have 2 comma 5 comma D. Okay. So now we will take out C because it is the front element of the priority queue. So we have taken out C. Okay. So now we will explore the neighbors of C. So the distance array we are maintaining, so A has a value of 0, B has a value of 1. So C now has a distance of 2. So we will update the distance of C as 2. Okay. So now we will go to the neighbors of C and C, that is F and G. So F will have a distance of 3, G will have a distance of 3. So if we see the elements which will be there, so we have 3 comma F now, and we have 3 comma G. Okay. So if I have to rearrange these elements in the priority queue, so it will be 2 comma E, 3 comma F, 3 comma G, and 5 comma D, because we are maintaining in the increasing order. And when you do this in a priority queue, this order will be maintained by itself, because in a priority queue things are always maintained in an increasing order. Okay. So now we will take out E. Okay. So E has a distance of 2. So now we will explore the neighbors of E, that is B and D. Okay. So if I means update the distance of D from E, what will be the distance of D? So it will be distance of E plus 1. So the distance of D is 2, so it will be 3. Okay. So we have a current distance of 5 for D. So 3 is less than 5. So we have found out a shorter path of D, right? So we will kick out this value of D, means we will not consider this value of D anymore. Okay. So we will kick out this value of D from the priority queue, and we will update the value of D as 3. Okay. So now it has a value of 3. Now again, if I go to B, so B is also a neighbor. So if I update, if I see the distance of B, so it is 1. Okay. And if I take DE plus 1, so it will be 3. So 1 is less than 3. So the current distance of B is shorter. Okay. So we don't need to update anything for B. B remains as it is. But for D, we have found out a shorter path, that if we go through E, we will be traversing a distance of 3. Okay. So we will cancel the current distance of D, that is 5, and now we will update the distance of D as 3. So now we have this many, means we have these elements in the priority queue. So if we arrange this in the increasing order, so this will be 3F, 3G, 3D, and so E is also taken out. So we have these 3 elements. Okay. So now we will take out F. So we also update the value of F as 2. Then we take out G, we update the value of G as 2, and we take out D, we update the value of D as 3. Okay, so this all will be 3, not 2. Sorry. So the value of F is 3, G is 3, and D is also 3. So if you manually calculate the minimum value, so A has a value of distance of 0 from A, B has a distance of 1, so that is this path. C has a distance of 2, that is this path. F and G has a distance of 3, that is through C. So F and G has a distance of 3, and E has a distance of 3. So if you go from A to B, then E, then you go to D, so that is 1 plus 1 plus 1, that is 3. So D has a distance of 3. So you have found out the shortest path from the source to every other node. Okay, so also if you see the order, so first we have traversed B. So we have taken out B first, then we went to C, then we went to E, then we went to F, G, and D. So the nodes which are closer to A are traversed before, and also we have found out the shortest distance of all the nodes from a single source. Okay, so this is the Dijkstra algorithm. So I think these four algorithms are enough for graph for any internships or any placement interviews. These four will be more than enough. If you practice questions well enough from these four topics or these four algorithms, I think you shouldn't have any more problem for solving graph questions for internships and interviews of full-time jobs. Okay, so I think that's it for this session. So uh, that's it for this session. So thank you for attending this session. I hope you liked it, and see you in the grand contest that will be coming up shortly.
Thank you so much, sir, for enlightening us with your knowledge and experience. It's a pleasure for all of us to be taught by you, sir. Thank you, sir, for giving us a valuable time and sharing your knowledge with us. Special thanks to GFG and Coding Minutes for being our title sponsor and educational partner. Now it's time for you guys. The link for quiz is in the description below. Check it out. Winners will get exciting prizes. So what are you waiting for? Hurry up and grab the prizes. And once again, thank you for everyone for joining the session. Bye.
So you think you know data structures well, but often get stuck when it comes to problem solving. Well, now you are at the right place. Welcome to Data Structures and Algorithms Level Up course. Hi, my name is Prateek and I'm a software engineer at Google. I have created this course for anyone who wants to learn how to apply data structures for solving coding problems and algorithmic optimization. In the past 5 years, I have taught over thousands of developers through my online and in person bootcamps that helped many students and working professionals in their careers immensely. This course will help you to develop a strong problem solving mindset and write cleaner and highly optimized code. This course is a highly practical course and we will discuss over 100 problems of varying difficulty levels along with a complete hands on implementation. You will learn various tips and tricks related to concepts like recursion, backtracking, sliding window, two pointer problems, dynamic programming, pattern matching, graph algorithms, and more. Not just that, you will also learn by solving problems involving various data structures such as stacks, queues, linked lists, heaps, hash tables, tries, and graphs. With over 200 plus high quality video lectures, concise and simplified explanations for complex topics, this course is your one stop destination to master problem solving. Unlike most other courses, this course is fully interactive. You also get coding exercises and multiple choice questions to test your skills. The code judge ensures that your logic is correct and you get a real time feedback on your code submission. Doesn't matter whether you have a computer science background or not. This course is for anyone who wants to ace problem solving and achieve big. So what are you waiting for? Sign up today and I'm looking forward to meet you in the course. So you think you know data structures well,